Start?
Yes, sir. Yes, sir.
Good morning. The title of my lecture today is Vacuum PVD Improvement, a case study of the second soft ground improvement at the third runway north extension of Suvarnabhumi Airport in Thailand. I am an emeritus professor of the Asian Institute of Technology. And I have my book a while ago about soft ground improvements, which is a pioneering book in ground improvements, which includes all the elements of ground improvement in one volume. In the right side, you can see the first page when you hit and access myself as the Google Scholar. For my lecture, I will always start that the soil is composed of particles and is composed of solids and voids. The particles consist of coarse-grained soils like sand and gravel. The volume is much larger than surface area. Gravity, force govern, and there's friction between particles. For fine-grained soils like clay and silts, surface area much larger than the volume, and there are electrical forces between the particles governs the behavior, and there is some cohesion or repulsion or attraction and cohesion. These are the elements of the ground improvement techniques. And the first is working on the soil. Ground improvements, you have to reduce the volume, reduce the voids so that we increase the strength and reduce compressibility. And if the soil is coarse grain, then we have to use compaction to reduce the voids, like vibroplotation, dynamic compaction. And if we have fine-grained soils, we cannot use force to reduce the voids. We have to use drainage, and where vertical drains or vacuum PVDs are used. So adding foreign materials to the soils, like reinforcements, this is for coarse-grained soils. We have earth reinforcements. And for fine-grained soils, we can add chemicals like cement and lime or polymers. The comparison of the cost of ground improvements, the PVD is the cheapest compared to sand compaction pile and deep mixing cement piles. Here is a map of Southeast Asia. Island is in the middle. And in Southeast Asia, we have Myanmar, Vietnam, Malaysia, Philippines. And the thickness of the soft clays in the central plain of Thailand, which is around 200 by 400 kilometers. Bangkok is in the middle here, and the Suvarnabhumi Airport is southeast, 30 kilometers southeast of Bangkok. You see the red color here, and the thickness around 14 to 18 meters. This is the north-south cut off of the soft Bangkok clay. You can see the thickness from 10 to 18 meters. And this is quite uniform in the sense that we can see no sand lenses in the middle of the clay. It's quite homogeneous in the sense, and it's good for research. This is the water content with depth. You have water content exceeding 100 because there is some 5% organic content. This is the undrained shear strength with depth. The lowest one is around 10 kPa. There is some problem because of the withdrawal of water from the sand aquifer below, underlying the steep clay and the soft clay. So there is the prismatic drawdown, and it reaches to around 10 meter depth. That's why and there is no need to drain out below 10 meters because it's draining by itself because of hydraulic connection. And then we can only install PVDs at 10 meter depth or 10 meters long. This is where it can be used, otherwise it will increase the rate of subsidence. Now, currently, the drawdown starts around 12 meters. This is a problem of subsiding ground. The pile-supported columns have differential settlements with the ground, surrounding ground. So for the soft clay, the voids are occupied by water. To reduce the voids, we have to drain the water out. And instead of the usual preloading by embankment, we put in artificial drainage paths, which are the vertical drains. And so shorten the length of drainage paths at the spacing of the PVDs. The conventional PVDs, we have used some berm to prevent slope failure, and takes a long time for that compared to the vacuum drain. So you see the PVDs composed of the core and the filter. The core is a channel of flow. The filter minimizes the entry of clay particles and reacts against lateral pressure. The pattern can be square or triangular. And for Bangkok clay is a shallow installation, we can use only modified backhoe. Here we have the installation using a modified backhoe. And by the installation of PVDs, there is some distorted zone, also called the smear zone, caused by the installation. And the permeability Ks is smaller than Kh. The degree of the smear depends on the ratio of Kh over Ks. So the distorted zone or smear zone is a function of the equivalent cross-sectional area of the mandrel that is used to install the PVDs. And it's well known that the diameter of the smear zone is twice the equivalent diameter of the mandrel. And this is the theory of vertical and radial consolidation. And the solution for that is a graphical solution and you can see here for vertical solution, vertical consolidation is the dash line, and for PVDs or horizontal flow is a series of curves. And so depending on n value, which is here, it's a ratio of the big D over small diameter, dW, of equivalent diameter of the drain. So we use the Hans-Bose equation for the solution of consolidation for PVDs. And we have here f sub n, f sub r, f sub s. F sub n is spacing, f sub s smear, f sub r is the resistance to vertical flow. This is equivalent diameter of the drain, the equivalent diameter of the drainage area for one drain. And this is the smear zone. This will come together for the solution according to Hans-Bose. This is the equation of Hans-Bose solution to the differential equation, horizontal flow. These are my papers on the PBDs, journal papers. And now we go to vacuum PBDs. Vacuum means we add vacuum force suction through the PBDs, and in so doing, instead of increasing the vertical load, we decrease the pore pressure to increase the effective stress. But the decrease of pore pressure or vacuum does not exceed atmospheric pressure, which is 100 kPa. So we can only apply vacuum from 90 to 95 kPa. So in this case here, we have atmospheric pressure loading in addition to the surcharge load. Here are my papers of the vacuum PBD journal papers. I get some reference from Chai, Professor Chai, my former doctoral student from China, for the crown deformation induced by vacuum consolidation. And here is the normal, vertical, and horizontal loading. Then add a vacuum here. The lateral movement depends on the magnitude of the vacuum compared to the original horizontal load. So if the vacuum is exceeding the loading from the vertical loading and horizontal loading, then we have tension cracks. The tension cracks is always there because the surcharge is always lower than the vacuum pressure. So Chai also in that paper derived the depth of the cracking. And in our case here, using these parameters, the depth of cracking can be as much as 4 meters depth. His paper also, Professor Chai, demonstrates if you have combination of vacuum and embankment. Embankment only, case 2. Here, the ideal is vacuum first and then embankment, so case 3. And case 3 here has the lowest lateral movement compared to case 3. Here, dash line, the largest lateral movement. I have some consolidometers, large scale at EIT. Here we applied one on the vertical drain, one in the PBDs with vacuum, the other one PBD with heat or thermal. And see here the PBD with thermal is one highest result in terms of increase of shear strength. This PBD only, and vacuum PBD is quite far from the thermal PBD. Here is the PBD only, vacuum PBD, and thermal PBD. And you can see that there is decrease of the time to consolidation using vacuum and thermal PBDs. This is the scanning electron microscope of before improvement is dispersive structure, and after vacuum become flocculated. So flocculated means we have increase in permeability and strength. Our project is around 30 kilometers southeast of Bangkok, this Suvarnabhumi Airport, Bangkok International Airport. The depth of thickness of soft clay is from 3 meters to 16 meters. But we install only the PBD at to 10 meters depth. And this area at the north part of the third runway, there was a first improvement in 2007, but that one is not enough. Using conventional PBD, the maximum pass pressure go only up to 80, 85 kPa. So second improvement done into 2021 using vacuum PBD. There's an installation of PBDs on the horizontal drains and connected to the perforated pipes. So this is the concepts. We have PVDs here, we have horizontal drains, you have airtight membranes protected by a geotextile layer to prevent puncture. And then you have the sand blankets. Then the sand blankets. Here is the air water separation tank distributed in the field. This separates the air goes to the main vacuum pump, the water goes discharged. And we have a sealing trench at the boundaries. Here is details of the improvement and all labeled here. This is the horizontal drain, perforated pipe connected to the vertical PVDs. And all the here the geotextile and geomembranes combined together at the top. This is more detail, the location of geotextile number 1, number 2, number 3, and we have the airtight membrane using HDPE 1 millimeter thick. And then we have the sand blanket, then the air water separator, and then connected to the main vacuum pump. You can see here the placement geotextile geomembranes, and you see the existing airport at the Suvarnabhumi Airport. And this is the air water separation tank, and the water is discharging, especially at the earlier part of the preloading. So we have what you don't see, but the airport runway, we have the base, sub-base, embankment, foundation, drainage system, the tarmac that consists the runway. The first improvement, these are the parameters obtained before the second improvement. And there is also the drawdown to 12 meters depth. So from there, the ground improvement was performed by C2 Thailand, where I am also a consultant. And we have here are the instrumentations. Instrumentation composed of inclinometers, settlement plates, piezometers, extensometers, dummy piezometers, and observation wells. And design, we have 1 meter spacing, square pattern, 10 meter long, and with airtight membrane, 5 months of preloading, 90% consolidation. This is the amount of loads, the vacuum about 70 kPa. And here is the start. Then when vacuum starts 5 meters, you have to stop pumping. And here we have the settlements up to 80 centimeters, 0.8 meters. And vacuum around 85 to 90 kPa. The pore pressure at the middle of the clay, 5 meter depth, around minus 73 kPa. Here is the settlement. And this is the rate of settlements. We stop at 2 millimeters per day. We stop the pumping about 5 months. These lateral movements, inward movements, creating some cracking, but it is located 6 meters away from the edge of the loading. And this is an observational method by Asaoka and by hyperbolic method. We compare, and all this we get at the three areas, RA1, RB2, TA1, the 9 degree of consolidation around 90%. So when we use the vertical drain, we look at because of the square pattern, you have the equivalent diameter, DE, capital D, and we have the equivalent diameter of the drain. We have the mandrel, equivalent diameter of the mandrel. The smear zone is ds equals 2 times dm, equivalent diameter of the mandrel. And the Hans-Boas equation is here. We have f sub n, f sub s, f sub r, and then Ks over Ks, 345. Here, 345. Ch, we get it. And the degree of consolidation is 90. So in that case, we have these are the data that we discussed earlier, smear zone and others. And the final settlement by one-dimensional consolidation was 0.8, similar to what was measured in the field. Hans-Boas equation, and we get CS value, and here degree of consolidation. The CS value, we can get it either by curve fitting, this here 4 meters squared per year, or we can use the equations of settlement equations. And this is the CS value obtained by the Asauka's method, using Asauka's method. And we can plot the CS over KS over KS, and these are DS over DM. DS is equivalent diameter of the smear, and DM is equivalent diameter of the mandrel for RA1, RB2, TA1. So here we can read off where is the CS value as a function of KS over KS. Since we have vacuum, KS over KS reduced from 5 ordinary PVD, conventional PVD, to 4 or 3. So in this case here, the back calculation, CS value, we have KS over KS of 3 and 4, equivalent to CS value of 3.76475 of RA1, RB2, and TA01. It floats around 4 for KS over KS equal to 4. So there is it. This is now the final one, the observed versus predicted settlements, calculated settlements, and the properties before and after. You can see the colored one is the after improvement, and there is a reduction of water content. The Atterberg limits not much change. Water with unit weight increase a little bit, and range strength almost multiplied by 2, and the maximum pass pressure increased to almost more than 100, from 85 to around 100. Actually, the second improvement, this almost is go up more than 100 kPa. So this is the table of first improvement compared to the second improvement. And you can see unranged strength increase, the pre-consolidation pressure from around 80 to 100 average. And the before improvement was only around 50 or 60. And range strength before improvement around 10, increased to around 20 after the first improvement, at 30, 31 to the second improvement. So the conclusion is given here, and I think I am out of time, so you can just read this. But you see CS value using DS over DM equal to KS over KS 5, but for vacuum PVD should be 4, and the CS value is around 4 meters squared per year. The unranged strength increase. And so thank you for your attention.